So now we discuss Gibbs Sampler. This is an algorithm initially developed by Gibbs, and in 1994, my PhD advisor Jun Liu and his colleagues used it first time for motif finding, and it was published in Science. It's probably one of the earliest statistical methods that was used for computational biology and published in Science. So Gibbs sampling uses a stochastic process to update these two parameters. Basically, given the input sequence and the genome background, it will iteratively estimate the motif location in the input sequence as well as the motif probability matrix. But it updates in a more stochastic way compared to the expectation maximization approach. And I will show you how this is done. So supposedly this is the input sequence, and this is where the original, the real motif occurs. But initially we don't need to know, we just kind of randomly start somewhere. Given the alignment, we can then construct a initial position weight matrix by looking at, for example, how many A's are there in the first position, plus a little pseudo count, divided by all the A, C, G, T's in that first position, and plus all the little pseudo counts for each of the bases. And of course, this is only the A in the first position in the matrix. We can use the same approach to fill the current matrix. Then we take out the first sequence out. And when this is out, the matrix will change slightly because this little fragment is now taken out. We now use the current matrix to score every little fragment in the first sequence that's taken out, and each will give us a score. So how do we give the score to each segment? Again, we use this likelihood ratio. Right? Given the sequence, we have the matrix, we calculate the probability of this particular sequence coming from each, this location in the matrix, divided by the probability of seeing the same word from the genome background. And so I want to show you an example. You can see here, this motif matrix is pretty weak. In the first position, we have 40% A, 20% C, G, and T. In the second position, we have 50% T, 20% GC, and 10% A, and so on. We can come up with a consensus, which is the highest based on every position. So the consensus is A in the first position, T in the second position, C in the third position, A in the fourth position, and G in the fifth position. And in this particular sequence, we do have an instance of A, T, C, A, G, which matches to the consensus. And you can see how this particular sequence is being scored. In the first position, it's 40% A in the matrix divided by 30% A in the genome background. In the second position, it's 50% of the T divided by 30% T in the genome background. The third position is 40% C divided by 20% C in the genome background, and so on. And you multiply all of them together, you will get a final score, which is pretty high. But if you look at, because in this long sequence, we are doing a window sliding of all the adjacent or the next 5-mers, you can just see one 5-mer before that. It kind of looks similar, but then basically at every position it's off base, right? And so the first position is still an A. You calculate the A in the first position divided by the genome background, but the second base in here, the A only have 10% divided by a genome background of 30.3. But then when you multiply each base together, you get 0.004. I mean, these two bases look almost the same, but in the final matrix, because this ATCAG is a correct match, it will actually have much better score than the adjacent one. And you look at the next 5-mer here, also you get a pretty small score. And so even if our initial matrix is not super strong, when we try to use this matrix to score every small word in the sequence, you get a variable score. And so supposedly we did have this score distribution. In Gibbs Sampler, in the next step is we sample a position to put the sequence back. By sampling, we mean the likelihood of picking a particular location is proportional to its score. So this really high scoring one might get picked at a higher chance, but the smaller one will also have chance, just smaller chance. So in this case, for example, we pick the second highest scoring fragment and we'll put it back. And with this, we can recount the total, the ACGT percentage at each position. Now our probability matrix will change slightly. So we can show you how sampling is done. When you can see this is different from a kind of a greedy type of approach. So supposedly, this is the score we are getting at each position. In order to do sampling, we calculate the subtotal at every position. And at the end, we get a sum, in this case of 47. And in order to do sampling, we do a random number generator from 0 to the final 47, and say it gives us an x. Let's just say x is 30. And then we'll just look into here, say, is it higher than 30? No, keep going. Is it higher than 30? No, keep going. And then here, oh, there, 38 is higher than 30, and that's the position we're going to sample, and that's 6, right? So you can see because the gap between 38 and 39 is very small, because the score is 1, we have a small chance of hitting the gap, right? The random number generation, right, hitting this 38 and 39, but we'll have probably more chance hitting on a random number because the gap between 4 and 6 is pretty high, we're more likely to hit it. And to show you with a more extreme example, we have another list of scores, and you can see this one has so much better score. And so once we do the random number generation from 0 to 546, it doesn't matter whether this random number is, if it's 100, we'll stop at position 7. If it's 200, we'll stop at 7. 300, we'll stop at 7. 400, it will stop at 7. 500 will stop at 7. It's only when you say you do a 542, then you will stop at position 8. Position 9, right? And so most of the time we're actually land in here. And that's how sampling works. So for Gibbs Sampler, every time we take out one sequence, the matrix will change a little bit. You use the Motif matrix to score every little word in the sequence that's taken out, and then use the sampling approach to pick a new position to align that sequence back to the current alignment. Then the matrix will change a little bit. Then you take out the next sequence. So we do this in turn, one at a time, one at a time, one at a time. And magically, this actually will get converged into some enriched motifs. And when we eventually converge, it's like this. The matrix has pretty strong preference. Say first position is a very strong A, second position is a very strong C, and third position is very strong G, or so on. Therefore, when you take a particular sequence out, when you score the different words, one sequence will shoot up, have much better score than the other. Then the next time when you sample back, it will come back to the same alignment. So it will converge when the matrix doesn't change so much, and the alignment, every time you pretty much go to the same place. And then that's when you kind of found the motif.